everyone. This is Mrs. Jackson. This is Chapter 2, Section 5. The title of this section is called Completing the Square. I'm going to put this entire section into one video. It may prove to be a little bit lengthy. Apologize for that. But I want to stay on topic instead of splitting up into multiple videos. Okay, so what are we doing in this video? We are going to learn about a technique called completing the square, which means we're going to create a perfect square where one doesn't exist. And the reason why we're going to do that is so that we can simply take the square root of something to solve a quadratic equation. This ends up being fairly convenient if we can't factor that quadratic equation. If you recall in the last section, I said that not all can be factored. So we're going to need more tools in the toolbox. Okay, so let's talk about what a perfect square is, first of all. A perfect square is any number or algebraic expression that is multiplying itself. So that's going to create a perfect square. For example, 2 times 2 is a perfect square. That creates 4. 10x times 10x is 100x squared. That's a perfect square. And so that phrase square comes from the area of a square. So if we had a square and we multiplied the side times the side, because all 4 sides are equal or congruent, then we would have the area equal side squared. And so that's where that phrase comes from. All right, so first let's look at a numerical example. So 5 times 5. 5 times 5, they're 2 numbers. Multiplying itself 2 times, we could write that as 5 to the power of 2, or 5 squared. That's 25, and that is an example of a perfect numerical square. Let's look at a monomial expression. By that I mean a one-term expression that is algebraic in nature. So let's look at 3x times 3x. We could write that as 3x squared. And remember, if I want to write 3x squared and I want that 3 to see the power of 2, to see that square, then 3x, the base, has to be in parentheses, and that would equal 9x squared. And 9x squared is considered a perfect square. Let's look at a binomial expression. Root word bi means 2. So let's look at something simple like x plus 4 times x plus 4. I could write that using exponents as x plus 4 squared. So if I saw something like x plus 4 squared, that's a perfect square. Now just as you know, side note, this turns into a trinomial. If we actually did the distribution of all the terms, we would end up with x squared plus 8x plus 16. Remember, we square that first term, we square the second term, and the middle term of the trinomial is twice the product of these two terms in the binomial. Okay, great. And then if we look at a trinomial expression, if I just wrote something such as 9x squared plus 12x plus 4, this is an example of a perfect square. Now, you might not recognize it as such right away, but we have a perfect square in the first term. We have a perfect square in the last term, and the product of the two terms in the binomial multiplied by 2 or doubled is going to equal 12x. So by that, let's write that out. We've got 3x times 3x would give us 9x squared. 2 times 2 would give us the positive 4, the constant, and then twice their product. So 3x times 2 is 6x. Twice their product is 12x. Now this is going to take some time to get used to, being able to spot a perfect square here when you're looking at the trinomial, but that's the goal. We're going to try to see that perfect square that creates it. Okay, before I continue with the notes, let me just show you what the goal is, what I mean by taking the square root to solve. So if we had something very simple like x squared plus 4 equals, I don't know, 20. If I had something like this, you would not be looking to factor this. You wouldn't move everything over into standard form. We don't have an x term here. All we have is constants in our x squared term. So hopefully you probably naturally, you wouldn't even think about it. To start to solve this, you would subtract the 4 from 20. And then to solve this equation, you would take the square root of both sides. And you would get, actually, let me put that in black. You would get x equals, and most of you would probably write 4, but as we've seen in the complex numbers, when we take the square root of positive 16, we end up with 2 roots, or 2 solutions, which is positive and negative 4. The idea behind completing the square is creating some kind of situation where we can just simply take the square root to solve, rather than go through all of the trouble of factoring. And so that's the technique I'm about to show you. Okay, let's first do a comparison of 2 different methods. The first method I'm going to show you is something you already know, solve by factoring. I've given an equation here, a quadratic equation that is solvable by factoring. And then I want to show you the exact same equation and solving it by completing the square. Okay, so let's go ahead and look at what we already know, which is factoring. We know we want to get 0 on one side, so I'm going to subtract this 9 here. And I have x squared plus 10x plus 16 equals 0. And a, in this case, equals 1. B equals 10. C equals 16. So we're looking for factors of AC. AC equals 1 times 16, which is 16, that sum to our B, which is 10. So we can go through all the numbers. 16 times 1, that gives us 17. 8 times 2, that gives us what we're looking for, our 10, etc. You can actually keep going with 4 times 4, and that gives you 8, but you get the idea. We're looking for the 2 factors that multiply to give you the 16 and sum to give you 10. We're going to rewrite that 10x using the sum of these 2 terms. It doesn't matter what order you put them in. I'll put 8x plus 2x. And I've got my x squared plus 16 equals 0. We're going to factor by grouping. And the greatest common divisor here in the first 2 terms is x. That would leave me x plus 8 left. And the greatest common divisor of the second 2 terms is 2. That would leave me with x plus 8, which is what we're hoping to see. And because these 2 terms are identical, x plus 8, that allows me to bring my x plus 2 together using the distributive property times x plus 8 equals 0. And the 0 product property allows us to bring both of these factors equal to 0 separately and solve for x. So I have x equals negative 2 and x equals negative 8. So this is an example of a quadratic equation that's factorable. And easy enough, we found our 2 solutions. All right, let's look at the exact same equation now from the idea of using or solving using square roots. So it may or may not be obvious to you, but this trinomial here I purposefully picked is a perfect square. So the way to identify that is first look at the first term. That's a perfect square, x times x. The constant c, that's a perfect square, 5 times 5. And if you look at that and try to see, well, is that going to give me the perfect square? So x here, I'll write it out as a product of two binomials here, x times x and then 5 times 5. Is that going to give me my 10x? And hopefully you can see that it does. So if we distributed, we're going to have one 5x and another 5x, and that's going to give us twice the product of these two terms, or the 10x there. So you can see that trinomial is a perfect square. Because I have a perfect square on the left side of this equal sign, I can just take the square root to solve. If I take the square root of the left side of the equal sign, I have to take the square root of the right side. And so what I have left is, of course, the square root of a perfect square. They undo each other. They are inverse operations of each other. So on the left-hand side, I just have x plus 5 coming out. On the right-hand side, the square root of positive 9 is both a positive and a negative 3. And so we can solve here. I've got x plus 5 equals positive 3. And I also have x plus 5 equals negative 3. And so over here, I'm going to subtract 5 from both sides. And I have x equals negative 2. And over here, I'm going to subtract 5 from both sides. And I have x equals negative 8. And so you can see that because we had a perfect square here, this trinomial was a perfect square, I could solve by just taking the square root, get the solutions very quickly. Or over here, I could solve by factoring and get the same solutions. Although the right side is a bit simpler, I suspect that you would prefer to solve by factoring because that's the technique and the method that you know the best. In the end, I think it's a matter of preference, and you should always solve in using the technique or the method that you think is easiest or that you feel most comfortable with. However, some quadratic equations cannot be factored. And so we are going to need to learn the completing the square method for those cases. All right, so going forward, I'm going to focus on how to create a perfect square where one doesn't exist. So to do this, we're going to make some observations after actually looking at the result of the square. And I'm going to do this fairly quickly. So x minus 2 squared, the first term gets squared. The second term gets squared. Negative 2 times negative 2 is a positive 4. And then the middle term is twice the product of the two terms. So that would be negative 4x. X plus 6. The first term gets squared. The second term gets squared. The middle term is twice their product. 6x times 2 would be 12x. X plus 3 squared. The first term gets squared. The second term gets squared. And the middle term is twice their product. Twice 3x is 6x. X minus 8 squared. The first term gets squared. The second term gets squared. Negative 8 times negative 8 is a positive 64. And the middle term is twice their product. So negative 8 times x is negative 8x times 2 is negative 16x. Now, I want you to get comfortable with this. I did that quickly, but remember, when in doubt, write it out. So if you ever were confused about where that middle term comes from, you would write out x minus 2 times x minus 2 and do all the distribution to see where that middle term comes from. Now, I want you to make an observation here. How does this b relate to c? So in every case, there's a pattern. And that pattern is the secret to us being able to create a perfect square. So in this case, b was negative 4, and c turned out to be positive 4. In this case, b was 12, and c turned out to be 36. b is 6, c turned out to be 9, b was negative 16, and C turned out to be positive 64. Take a moment, even pause this video. See if you can see a pattern here, the relationship between B and C. Are you able to see a pattern in every case? The pattern is that C, whatever that C value is, it turns out to equal half of B squared. So if you look at this very carefully, in this first example, B is negative 4. If we divide B by 2 and then square it, we've got negative 4 divided by 2 squared equals positive 4. Next example, we have 12 divided by 2 squared is 6 squared, which is 36. We have 6 divided by 2 squared is 3 squared, which is 9. Finally, we have negative 16 divided by 2 squared. We have negative 8 squared, which turns into 64. So this is the big concept here. If we were given two terms here and we wanted to make a perfect square where one didn't exist, we would take half of this coefficient in front of the x term and then square it, and that would create our c term, and then that resulting trinomial would be a perfect square. Okay, let's use this concept and practice making a perfect square. So I've got 3 examples here up top, and they're not complete. So we have x squared minus 4x is our first example. What can we add there for our c term that's going to create a perfect square? So what we just observed on the previous page is if we take half of b, b in this case equals negative 4. If I take half of b and I square it, that's going to equal my c. Half of negative 4 divided by 2, that's negative 2 squared. That equals 4. So if I add 4 here, I'm creating a perfect square. And I can rewrite that as x plus 2 times x plus 2, or x plus 2 squared. If I have b here equal to positive 9, so b equals 9. If I take half of 9 and I square that, that's going to equal my c. If I square 9 halves, I get 81 fourths. So if I add 81 fourths here, that creates a perfect square. That's x plus 9 halves times x plus 9 halves. That middle term is going to be twice the product of these two here. So the product is 9x halves. If I did twice that, that would give me 9x. And so my perfect square is x plus 9 halves squared. All right, last example here. I have b equal to 1/2. I'm going to take half of 1/2. So I've got 1/2 divided by 2, and I'm going to square that to give me my c. 1/2 divided by 2 is 1/4. If I square 1/4, I get a c equal to 1/16. So if I add 1/16 here, my perfect square becomes x plus 1/4 times x plus 1/4 is going to give me this x squared plus 1/2 x plus 1/16. I can rewrite that as a perfect square. So what I didn't point out, but maybe you can observe here, is that in every case, my coefficient in front of the x squared term was 1. And that becomes a very important point in completing the square. So make a big note for yourself here. A must equal 1. So in every case, when we go to solve equations, we're going to force A equal to 1 in order to complete the square. And finally, just make a big note here. C equals half of B squared. So this is the key to completing a square. Okay, so the first example we're going to take a look at is easily factorable. So I wanted to start with something easy. I think you can see A times C is 11. The factors of 11, there's only one set of factors of 11, which is 11 times 1, and they sum to 12. So this equation, absolutely, we can factor it. But I wanted to start with something like this to show you this complete the square technique, and then we're going to move on to other equations that cannot be factored. So first things first, is A equal to 1? So please write that as a note. A has to equal 1. If it does, you're good to go. If it doesn't, we have to divide through everything by that A to make sure that A is 1. All right, so in this case, check. We've got A equal to 1. And counter to what we usually do when we factor, we move everything to the left, 0 on the right. In this completing the square technique, we're going to do something opposite, which is get that constant out of there. So we're going to subtract the 11, and we're going to get that over to the right. And we're going to have the x squared term and the x term over here on the left. And we're going to have our negative 11 over here on the right. And so the idea here is make a perfect square over here to the left where 1 doesn't exist. So we are going to want to add something here to this left side in order to make a perfect square. And as we just talked about, that C that we're going to add is going to be half of B squared. So in this example, we've got 12 for our B. We're going to take half of that and we're going to square it. So we've got 6 squared is 36. So we're going to add 36 here on the left in order to make a perfect square. If we add 36 to the left side of the equal sign, we have to add the 36 to the right side of the equal sign in order to maintain equality. So whatever we do on one side of the equal sign, you got to do exactly the same thing on the other side. And so what we end up here on the left is we have a perfect square. We have x plus 6 times x plus 6. We can write that as x plus 6 squared. And what we have on the right side is we have 36 plus 11 is 25. So we have this x plus 6 squared equals 25. The inverse operation of squaring is square rooting. So if I square root the left side, I got to square root the right side, and I end up with inverse operations. They cancel. X plus 6 comes out of the radical, and the square root of 25 is both positive and negative 5. And so I have x plus 6 equals positive 5, and I have x plus 6 equals negative 5. And one solution is 5 minus 6 is negative 1. And the other solution is negative 5 minus 6 is negative 11. So those are our two values of x. We could have solved this by factoring, but I just wanted to show you an easy case on how to complete the square. All right, let's take a look at the next example. 3x squared plus 12x equals 27. First thing to note is a does not equal 1. A does not equal 1. So we have to divide through everything by that A in order to make A equal to 1. And in this case, it turns out to be kind of easy because everything is evenly divisible by 3. So we have x squared plus 4x equals 9. If you want to move the 9 over, you can. Subtract 9 from both sides. Try to factor it. So look for factors of 9 that sum to 4. And I think you're going to quickly see there are none. So it's not going to be factorable. There are no two numbers that we can multiply together to give you -9 that are going to sum to give you +4. So this is an example of an equation that is not factorable. So consequently, we're going to go ahead and move that C back over to the right-hand side so that we can make a perfect square on the left side. So on the left, that was my dog who just did a huge sneeze. On the left, we have x squared plus 4x equals 9. And we're going to want to try to create a perfect square over here. So we look at b, so c is going to equal half of b squared. And so we have 4 divided by 2 squared is going to give us another 4. So to make a perfect square on the left, we're going to add 4. If I add 4 on the left, I've got to add 4 on the right. Notice I'm putting these in boxes. I'm trying to make it very obvious to my eyes that I need to maintain balance and equality. So on the left, we have x plus 2 times x plus 2, which is x plus 2 squared. And on the right, we have 13. 9 plus 4 is 13. So I'm going to take the square root of both sides to solve. Inverse operation of squaring is square root. If I do that on the left, I got to do that on the right. And I have x plus 2 coming out. And on the right, I have both the positive and the negative square root of 13. So if we keep going here, I've got x plus 2 equals positive square root of 13. And I have x plus 2 equals the negative square root of 13. Square root of 13 is an irrational number. So we have to agree on some kind of approximation. We're going to use our calculator. We're going to approximate to something. I recommend for a low number like this to the 100th place. So we have x equals square root of 13 minus 2. And that is approximately, you can approximate the square root of 13. And the square root of 13 minus 2 is approximately 1 61/100ths. And over here I have x equals the negative square root of 13 minus 2. And that would be approximately negative 5 61/100ths. So this is an example where we would never be able to factor this. The solutions are actually irrational because we're taking the square root of a non-perfect square. And so this is a case where we would have to complete the square in order to find those x-intercepts. They are real, however. These numbers will cross that x-axis. So they are not complex numbers or imaginary numbers, rather. They're crossing that real axis, that real x-axis. But they're just not numbers that we would be able to factor. Okay, last example. I purposefully picked solutions that were going to result in complex numbers. So the first thing you would look at here is, can I factor this? And a times c is 34. You can try to factor it. So we've got 34. We're looking for factors of 34 that are going to sum to -8. And if you look at all of the factors of 34, 34 times 1, I guess 17 times 2 really is it. You're not going to end up with any kind of combinations that's going to result in -8. So quickly you're going to realize I cannot factor this. And so we need to get that 17 over to the other side so that we can try to create a perfect square here. So we have 2x squared minus 8x equals -17. And the important thing here is that a has to equal 1. It's just so much easier to create a perfect square. So we're going to get rid of that 2 out front there. If I divide through by 2, every term has to see that division. So I've got x squared minus 4x equals -17/2. And you can leave it as -17/2, although I suspect a lot of you might want to turn that into a decimal. It's completely up to you what you want to do. If we do turn that into a decimal, we would end up with -8.5 over here. Okay, so we want to create that perfect square on the left-hand side. So we want to find some value of c we can add over here to make a perfect square. And if we add that on the left, we're going to need to add that on the right. And so, again, the value of c that's going to make a perfect square is half of b squared. So we have half of -4 squared, and that's going to give us -2 squared is +4. So on the left, I'm going to add +4 to create a perfect square. And if I do that on the left, I'm going to need to do that on the right. And so on the left-hand side, we have x minus 2 times x minus 2. That's going to give us that perfect square. That's the same thing as x minus 2 squared. And on the right, we have -4.5. And so when you see that we are ultimately going to be taking the square root here, undo a square with a square root, and you see we're taking a square root of a negative number, then immediately we have to think, okay, we're going to have imaginary or complex solutions. So square root of a perfect square, we just end up with the x minus 2 coming out. Over here, we're going to have the positive and negative square root of 4.5. And that negative here, the square root of this negative, is going to give us that I, that imaginary unit coming out. And so I have x minus 2 equals the square root of 4.5 I. And I have x minus 2 equals negative square root of 4.5 I. Okay, so to finally solve for these complex solutions, I'm going to add 2 to both sides over here. So I'm going to add 2, so I'll have a positive 2, and I have the square root of 4.5 I, and I'm going to add 2 to this side as well as to this side. Notice I'm putting the real part first. Remember when we talked about writing complex numbers, we like to write the real first and the imaginary second. And we could approximate these if we wanted to take the square root of 4.5. I could say that this is approximately 2 plus, I recommend going to the 100th place again. And over here we'd have x equals 2 minus 2 and 12/100ths I. So as soon as you see complex solutions, we know this parabola would never cross that x-axis because that's a real number line. So this would be an example of a parabola that's it's actually upward facing, and it's going to be up in one of the quadrants 1 or 2 and never touch the x-axis. Okay, so in this video we learned about how to complete the square. By doing so, we create a perfect square where 1 doesn't exist, and we solve the quadratic equation by taking the square root. And this is a technique that we're going to need to use if our solutions are irrational or if our solutions are not real. In other words, they are complex. This is going to take some practice, but I hope this video helps. Thanks for listening.